Welcome to today's paper reading. Today's paper is titled, LongCite, Enabling LLMs to Generate Fine-Grained Citations in Long Context QA. This paper was published on the AR14 preprint by Jiajie Zhang and colleagues from Tsinghua University and Jipu AI. The abstract highlights a significant issue with current long-context large language models, LLMs, which is the lack of citations in their responses. This makes it difficult for users to verify the information, raising concerns about the model's trustworthiness due to potential hallucinations. To address this, the authors introduced LongBench-Cite, an automated benchmark for assessing LLM's performance in long-context question answering with citations. They also propose a novel pipeline called CoF, which helps in generating long-context QA instances with precise sentence-level citations. This pipeline is used to construct the LongCite 45K dataset, which is then used to train the LongCite 8B and LongCite 9B models. The evaluation results show that these models achieve state-of-the-art citation quality, outperforming advanced proprietary models like GPT-4o. Additionally, the use of citation information in training effectively reduces hallucinations and improves the uniform utilization of context. Recent advancements in long-context large language models, LLMs, have enabled them to handle lengthy text exceeding 100,000 tokens, addressing various user questions such as information extraction and summarization. However, these models typically do not provide citations to specific context snippets, making it challenging for users to verify model outputs. This lack of citation support significantly impacts the reliability and trustworthiness of long-context LLMs, especially given their struggles with hallucinations and tendency to generate unfaithful content. To address these issues, this work introduces LongBench-Cite, an automatic benchmark to evaluate LLM's performance on long-context question answering with citations. Additionally, the CoF pipeline is proposed to construct high-quality long-context QA instances with precise sentence-level citations, leading to the creation of the LongCite 45K dataset. These innovations aim to enhance the capacity of LLMs to generate accurate responses with fine-grained citations, thereby improving both citation quality and response correctness. The task of long-context question answering with citations, LQC, is formalized as follows. Given a long context E and a query Q, the language model, LLM, is required to return a response A, which consists of N statements. Each statement SI cites a list of snippets CI from D. In this work, LLMs need to segment their responses into statements based on semantic integrity. Two types of citations are considered: chunk-level citations, where the context is divided into index chunks, and sentence-level citations, where the context is divided into indexed sentences using NLTK. The evaluation of LQC focuses on two dimensions: correctness, which assesses whether the response is accurate and comprehensive for the query, and citation quality, which evaluates whether the response is entirely supported by the cited snippets. Metrics include citation F1, which combines citation precision and recall, and citation length, which measures the granularity of citations. Additionally, a new metric, correctness ratio, CR, is introduced to investigate whether adding citations improves or degrades models' long-context QA performance. Table 1 provides an overview of the datasets used in LongBench-Cite, detailing the origin of the context, the average length of the context in English and Chinese datasets, and the number of data points. The datasets include multi-field QAN/CH, hotpot QA, doReader, GovReport, and LongBench-Chat, covering tasks such as single-doc QA, multi-doc QA, summarization, and real-world query. The average length of the context ranges from 4,559 to 35,571 words or characters, and the datasets are available in both English and Chinese languages. Figure 1 illustrates the difference between chunk-level and sentence-level citations in long-context question answering. Chunk-level citations divide the context into fixed 128 token segments, each cited using a chunk index. In contrast, sentence-level citations use NLTK to index sentences, allowing for finer-grained citations that can span multiple sentences. This method ensures better semantic integrity and user-friendliness, making it easier for users to verify the cited information. Table 2 presents the citation recall, precision, F1 score, and citation length for various models evaluated on LongBench-Cite using the LCS strategy. The metrics are crucial for assessing the citation quality of the models. Citation recall indicates the proportion of correctly cited statements. Precision measures the accuracy of the citations, and F1 score is a harmonic mean of recall and precision. Citation length quantifies the granularity of citations, with shorter lengths indicating finer-grained citations. The table highlights the best and second-best results, providing a comparative analysis of the model's citation capabilities. Table 3 presents the correctness metrics in the LQC setting using the LCS strategy, including correctness in the vanilla long context QA setting, CLQA, and the correctness ratio, CR, of various models on LongBench-Cite. The table highlights instances where adding citations improves or hurts correctness, marked in green or red respectively. Figure 2 provides an overview of the COEF pipeline, which is designed to enhance the citation quality in long context question answering. The pipeline is divided into 4 main steps. First, it generates a long context QA instance using self-instruct. Second, it retrieves K-context chunks based on the answer and generates chunk-level citations. Third, it extracts sentence-level citations for each statement from the cited chunks. Finally, it filters out LQC instances with insufficient citations. This process aims to ensure that the citations are both accurate and finely grained, supporting the statements effectively. The COEF pipeline for constructing high-quality SFT data for LQC involves 4 main steps. First, QA instance generation creates long context QA pairs. Second, chunk-level citation generation retrieves and cites relevant chunks. Third, sentence-level citation extraction refines these citations to pinpoint exact supporting sentences. Finally, data filtering removes instances with insufficient citations to ensure factual grounding. The pipeline was validated on LongBench-Cite, showing high citation F1 and correctness with a small citation length, outperforming other LQC strategies. Table 4 presents the performance metrics of various long-form question answering with citation, LQC, strategies on the LongBench-Cite dataset using GLM4. The metrics include citation F1, correctness C, correctness ratio, CR, and citation length, CL. The table consolidates results from multifield QAN and multifield QAZH for brevity. These metrics are crucial for evaluating the effectiveness and precision of citation generation in long-form QA tasks. In this section, the authors discuss the training and experimental results of their models, LongCite 8b and LongCite 9b. They selected 2 open-source base models, GLM4-9b and Llama 3.1-8b, which support a context window of 128K tokens and were suitable for SFT on LQC data. The training involved using 4 nodes with 8 times H880G GPUs, employing Megatron LM with context parallelism, and setting a batch size of 8 and a learning rate of 1 times 10 to the power of -5 for 4,000 steps. The experimental results showed that LongCite 8b and LongCite 9b achieved the best citation qualities among all models, improving overall citation F1 scores compared to proprietary models like GPT-4o and Claude 3 Sonnet. Additionally, SFT with citation information significantly boosted the long context QA correctness, with LongCite 8b/9b showing a 16% per 28% increase in correctness over long SFT 8b/9b. Table 5 presents the performance metrics of various models trained with different datasets on LongBench-Cite. Key metrics include recall, R, precision, P, and F1 score. LongCite 9b, with standard SFT, shows significant performance with R equals 57.6, P equals 78.1, and F1 equals 63.6. The table also highlights the impact of data filtering, where models without data filtering show notably lower performance. R equals 6.3, P equals 15.6, F1 equals 7.6. Additionally, the use of post-RACS data results in R equals 50.6, P equals 57.2, and F1 equals 50.1, indicating a substantial effect on citation quality. Figure 3 illustrates the correlation between the correctness of LongCite 9B's responses and their citation quality, as measured by the F1 score. The figure shows the mean and standard deviation of citation F1 for responses grouped by their correctness levels. It reveals that responses with higher correctness generally exhibit higher citation qualities, indicating a mutually enhancing relationship between these two attributes. Table 6 presents the citation quality evaluation of models on LongBench-Cite, assessed by human experts, GPT-4o, and ALC. The evaluations show consistent relative rankings among the models, indicating that improvements in GPT-4o scores reflect human preferences. However, there are discrepancies in absolute scores, with GPT-4o generally scoring lower than human evaluations due to unclear pronouns and cited snippets. This suggests potential for a NAFRA resolution to improve alignment, but at increased evaluation costs. Table 7 presents the agreement metrics between GPT-4o ALC and human evaluators. Key points include the Cohen's kappa coefficients, which measure the agreement for citation recall and precision. GPT-4o shows a substantial agreement with humans, particularly in citation recall, kappa equals 0.593, and precision, kappa equals 0.655. Additionally, GPT-4o achieves high accuracy in recall, 75%, and precision, 88.8%, when compared to human annotations. In the realm of long-context large language models, LLMs, a common approach involves further pre-training on extensive long texts and aligning these models with diverse long-context question-answer pairs. However, due to the challenges in obtaining annotated data, much of this QA data is automatically synthesized by the LLMs themselves, which can lead to issues with the faithfulness of the answers. This poses a significant problem, especially in sensitive domains like law and finance, where the accuracy and reliability of information are paramount. Our work addresses this by enabling long-text models to produce responses with fine-grained citations, thereby enhancing their verifiability and trustworthiness. In this study, the authors aim to improve the ability of large language models, LLMs, to generate detailed citations from extensive contexts. They introduced LongBench-Cite, an automated benchmark, to assess the current limitations of LLMs in long-context question answering with citations, LQC. Additionally, they developed the CoF pipeline, which leverages existing LLMs to create long-context QA instances with precise sentence-level citations, resulting in the LongCite 45K dataset. This dataset was used to train LongCite 8B and LongCite 9B models, enabling them to generate accurate responses and fine-grained citations in a single pass. Comprehensive analyses and human evaluations confirm the effectiveness of this approach. The authors believe this work establishes a strong basis for future research in LQAC and contributes to the advancement of more reliable and trustworthy LLMs. Thank you for watching.